Good morning. Welcome to the last lecture of this course, and in this lecture we will be talking about fading channels. Okay? And today we will see what happens when we go to wireless domain. Okay? So, let us try to see what happens when you have a wireless transmission medium. Let us assume that we have a transmitter Tx and a receiver Rx. Transmitter transmits some signal and this signal is received by the receiver. But because this transmission happens through electromagnetic waves, this signal may take different paths to reach a receiver. Okay. So, here I have shown two paths, right, but there would be infinite paths between transmitter and receiver. If I look at one of the path, then what would happen because of this transmission media is that my signal will get attenuated with some constant ai, and this signal will be delayed with this time unit, okay, tau I. So, what I say is ai is attenuation in ith path and tau I is the delay in the ith path, okay, and the channel in this path will create these two effects, namely it will attenuate the signal and it will delay the signal because of the propagation delay. Okay. Now, similarly you can envisage that this path will also create certain attenuation, let us say aj, and it will create certain propagation delay which I say as tau j. Okay. And now you can see as what is happening is that the signal is reaching the receiver at different time instances. For example, this signal will reach the receiver at tau I time instance and this signal will reach the receiver as tau j time instance. Okay. So, how can I think about the channel? So, I can think about the impulse response of the channel as this, and where this would have contributions from L paths. Let us assume that there are L paths between a transmitter and receiver. This L might be pretty large number, it might tend towards infinity. Okay. So, in each path the attenuation is ai and the delay is tau I, okay, and this is the impulse response of the passband channel. So, here the P represents that this is a passband channel. So, that is what happens typically in a wireless communication. Okay. So, the way to start modeling your channel is by assuming that there are infinite paths or large number of paths between a transmitter and a receiver, and you can think that in each path the effect would be that your signal will be attenuated by a certain constant and it would be delayed by a certain propagation delay. Okay. And the net effect will be the sum of the individual effects. If I have to think about the received passband signal, the received passband signal can be obtained by convolving the input with the impulse response of the channel. Okay. This is clear, we have been doing this all the while. Now, if I want to think about this passband signal, this passband signal can be thought in terms of the baseband signal. So, xbt is the baseband signal. Now, so this passband received signal can then be obtained by convolving this xpt with hpt. So, this is xpt represented in terms of the baseband signal and this is hpt. Okay. We have seen this. Now, if you convolve this with this, what would happen is simply that this signal which was at t will shift to t minus tau I. Okay. We have seen the impact of convolving a signal with an impulse. The only effect that it has is it shifts the signal to the time where the impulse exists. So, this impulse exists at tau I. So, this signal will also shift to tau I. Okay. So, now changing this t to t minus tau I, we get this, and then I have to change this t to t minus tau I and I get two complex exponentials. Okay. So, this is actually your ypt. simple. Okay. Now, to solve this further, I am making an important assumption here. I am making an assumption that x b t minus tau I is approximately same as x b t, and this assumption is known as narrowband assumption. This assumption is true in what is known as flat fading channels or in narrowband channels. So, in narrowband channels you can approximate the signal x b t minus tau I as simply x b t, and what it simply means is that if the symbol time of the signal is much larger than this tau I, then its effect is negligible. For example, if I have a signal whose symbol time is pretty large, and if I shift this signal with a very small delay tau I, so this signal shifts like this, then actually you can treat this signal same as this signal. Okay. This is the idea behind narrowband assumption. That means, if the data rate of the signal is pretty small, then this narrowband assumption holds. If the data rate of the signal increases, then this narrowband assumption might not be true. So, what we can say is, if the symbol time is much greater than tau I, where tau I is the delay created by a path of the channel, then I can simply use this narrowband assumption. Okay. Now, using this narrowband assumption, I can write y p t as simply this. So, what I did is I simply have changed x b t minus tau I as x b t. Okay. Now, if you think carefully, then this is actually y b t, because this is a passband signal. This passband signal can also be thought in terms of its baseband signal. So, I can think about this y p t as also real part of root 2 y v t times e to the power j 2 pi f c t, okay, and y p t is this. So, I can simply say that y v t, which is the baseband equivalent of this passband signal, is simply this thing, okay, which I write it like this. Now, because x b t is not a function of I can also pull this out of the summation, and I can simply obtain that y v t is simply x b t times this quantity, and this I call as h, which denotes the channel gain. Okay. So, I take this quantity and I simply call as h. Now, this h is not a function of time, right. So, it is a constant with respect to time. So, I can write this y v t is simply x b t times h. Okay. So, h, remember, is the channel gain, and this channel gain is still time invariant. Okay. Now, so what we have seen that h is simply this quantity. So, it is sum of the channel gains of each path, and there are L paths. Now, in general, this h is going to be a complex quantity, and it can be a complex quantity because we are thinking about the baseband signals. Okay. Baseband signals can be complex signals, right. So, h in general is a complex quantity because of this term sitting over here. So, I can write this h as simply x plus j y, okay, where x is simply this thing. So, I have broken down this complex exponential using cos and sine. So, I get x as simply this thing and y as simply this thing. Okay. Now, what is this quantity? So, you have several random variables here, and this is a sum of large number of independent random variables, and we have seen in one of the previous lectures that if you have sum of large number of independent random variables, by central limit theorem the resultant random variable will be a Gaussian random variable, and hence this x is a Gaussian random variable. Similarly, y is also a sum of large number of independent random variables, and hence y is also a Gaussian random variable. Why these random variables are independent? Because we are assuming that the attenuation and the delay of each path is independent of the another path, and hence each term will be independent of the another term, and hence x and y are sum of large number of independent random variables, and by central limit theorem they will tend to be Gaussian. Now, we can define g, which is mod of h, and thus the random variable g is simply square root of x square plus y square, and this is what we have seen before. G is a Rayleigh distributed random variable, and if I want to think about the phase of this h, the phase of the h is simply tan inverse y by x, and this we have seen that this phase of h is a random variable which is a uniformly distributed random variable. So, this is what we have seen in the last lecture as well. Let us revise this Rayleigh distribution. So, we have seen that the probability density function of Rayleigh distribution looks like this, okay. And if you assume the variance to be half, then the probability density function of the Rayleigh distribution looks like this, okay. So, for the derivation in this lecture, we will assume that the variance is simply half, okay. Now, with these assumptions, let us see if we can think about the performance evaluation of binary phase shift keying. So, let us look at what happens in the baseband domain. So, in the baseband you are receiving a signal ybt, which is simply the transmitted baseband signal xbt multiplied by this h, okay, or complex channel gain. Now, we have seen that this h induces a random phase because its phase is uniformly distributed. So, there can be any phase angle which this h can assume, and thus this ybt also can have any phase. Now, thus you know that if you want to detect BPSK, the information lies in phase. So, this signal might have a phase of 0 degree, or this signal might have a phase of 180 degree. Now, if this h induces a random phase, then this ybt also has a random phase, and thus the detection of xbt is not possible, okay. And thus when you want to use these modulation schemes which embed information in phase, the only thing you can use them is by learning what this h is. If you know what this h is, then you know what the phase this h creates, and then you can detect xbt. So, one of the assumption that we have to make is when we are detecting these modulation schemes where information embed in phase, is that we have to know what the channel is, okay. So, this channel estimation is must. How can we estimate channel? Okay. This is a very simple ideas. There are more sophisticated ideas of estimating channel which we will not look into, but simply what you can do is you can send a probing signal n times, okay. So, I can think about this, I am transmitting a signal A, then I transmit a signal A, then I transmit a signal A, then I transmit the signal A, and I transmit a particular signal n times, and receiver also knows that I should be receiving this signal A, okay. So, you decide a time frame in which you transmit a known sequence to the receiver, receiver knows what it should be expecting, and let us assume that we are transmitting that probe signal which has the signal value of A. What receiver receives is A h plus n1. So, this A multiplies by this h, some noise x, we call the sample of that noise as n1, and similarly it receives n such values. What the receiver can do is simply it can take the sum of these n values and it can divide by n, okay. So, what it would get is A h plus this thing, and what is this? This is the mean value of noise, and the mean value of noise is 0. So, the value of r that receiver would see then is simply A times h, and from this receiver can estimate h by dividing this r by A. So, R is known because these samples are known. So, it can sum up these values of these samples. So, R is known to the receiver, A is also known to the receiver because receiver knows what transmitter would be transmitting, and from this the receiver can estimate the value of H. Of course, this problem is really simple and trivial because what we have assumed is that this H remains constant across symbols. That means channel does not vary across symbols, all right, and in reality this will not be the case, and thus this problem is little bit more complicated than what we have presented. Okay. So, what we are saying in this case is, let us assume that the channel remains constant for certain time, okay, and in that time duration I am transmitting n symbols. By receiving the samples values corresponding to n symbols, and by summing them up and by dividing by n, receiver will simply receive A times H, where A is the numerical value of the probe signal and H is the channel gain, and thus from R receiver can simply calculate H. Okay. So, the point is, when we are thinking about these modulation schemes, H must be known. All right. Let us look at one small point. Now, what receiver is receiving? Let us say it is receiving a random variable V, which is not important how you call this random variable, because we will not be using this random variable anymore in this lecture. So, I could have called this anything. I have called this as V, which is simply A times H plus a Z. And what is this Z? Z is a proper complex quotient random variable. H is complex, right. That means we are thinking in the baseband domain. So, Z should also be a proper complex quotient random variable. H is also a proper complex quotient random variable. These complex quotient random variables are always this proper complex quotient random variables, and thus I simply also call them sometimes complex quotient random variable, okay, because whenever you see that this is a complex quotient random variable, it has to be a proper complex quotient random variable, because I and Q channels has to be independent, and it is also a good assumption to assume that noise in these channels is also identically distributed. Okay. So, anyways, so what I am receiving is A times H plus Z. Now, we have seen in AWGN channel we like to think about this energy per bit, and in case of BPSK this is simply A square. Okay. Now, in these fading channels, what is this energy per bit? It is A square multiplied by mod of H square, and if I call G as mod of H, the numerical value of G I call as a small g, and thus energy per bit in fading channels is simply A square times G square, okay, where G is the numerical value of random variable capital G, and where this random variable capital G is simply mod of H. Okay. So, what happens in fading channel is your energy per bit changes by this channel gain. Okay. Now, if you have to think about the performance of binary phase shift keying, we have seen in one of the previous lectures that probability of error in case of BPSK is Q of under root of 2 abno, and in case of fading channels this EB becomes EB times G square because of the reasoning that we have seen. So, this is the probability of error given a value of G, but G can take any value, and thus to find out the average probability of error you have to multiply this quantity with the probability density function of random variable G taking in a numerical value small g, and then you have to integrate this thing over all possible values of G. G lies between 0 to infinity because it is a mod of H. Okay. Now, when we have to solve this, let us look at the bound of this expression. We know that the probability density function of G is this, and we can use one identity that Q of x is always less than 1 by root 2 pi x e to the power minus x square by 2. Okay. So, this will give me substitution of this thing in place of q of x will give me an upper bound on the probability of error. So, substituting q of x as this thing and multiplying by this thing, we can get an upper bound on the probability of error. Okay. Now, let us try to see how can I solve this up. So, this cancels with this 2 cancels with these 2 2's, okay, and I can combine these 2 terms. What I get is this expression. Then I can substitute g times under root of 1 plus abno as simply x. If abno is pretty large, I can approximate dg as simply dx by root of abno. I can replace this thing by e to the power minus x square, and I can replace this dg by dx divided by root of abno, and I can solve this up. I can combine this abno with this abno, and I can solve this up to this expression. And I can solve this integration also by thinking this as Gaussian PDF, and by knowing that integration of Gaussian PDF from minus infinity to plus infinity is 1. Okay. Using these ideas, try to think about what is the value of this integration. I have given you a hint. So, you know that this looks like a Gaussian PDF, and you also know that if you integrate the Gaussian PDF from minus infinity to plus infinity, you should get a 1 because it is a PDF. Okay. So, using this, solve this, and what you get is probability of error should be less than 1 by 2 abno. If you do it exactly, what you can see is probability of error will be approximately 1 divided by 4 times abno. And let us see what is the abno requirement if we want to achieve a bit error rate of 10 to the power minus 8. Okay. So, if I want to think it, so abno will be 10 to the power 8 divided by 4, and this is a pretty large abno that we need to have. So, what we see now is that in fading channel the probability of error varies proportionally to 1 by abno, and for low error rates the abno requirement is pretty large. Okay. So, if we want to think about this increase in dB, the abno requirement would be around 74 dB. Okay. In AWGN channel, this abno requirement was 12 dB. In fading channel, the abno requirement increases up to 74 dB. Okay. So, in fading channel, that is the problem. The abno requirement increases to pretty large values, and thus it prohibits the use of these simple modulation schemes in case of fading channels. We need to do something else to improve the probability of error. So, let us try to summarize this. The performance of BPSK in AWGN channel was this. In Rayleigh channel, this becomes 1 by 4 times abno. For PPM, the performance in AWGN channel was this. This we have seen when we have looked at the performance of PPM in AWGN channel, and this is rather 2 PPM, okay, binary PPM, right. And in case of Rayleigh, this will simply be 1 by 2 abno. Using the same ideas that we have used for calculation of probability of error of BPSK in Rayleigh channel, you can simply use those ideas, solve that integration and things like that, and you will get that the probability of error of PPM in Rayleigh channel is simply 1 by 2 abno. Okay. You can also relate this to these coefficients. So, let us plot these curves. So, in AWGN channel, we have seen that the bit error rate decreases following a waterfall curve with SNR, but here in Rayleigh channel this is a linear decrease. If you plot the SNR in dBs and bit error rate in log scale. Okay. So, this decrease in Rayleigh channel is much smaller than the decrease that we could have in AWGN channel. Let us move on, and before trying to think what we can do, let us also estimate the performance of PPM in non-coherent systems. So, we have seen just now the performance of BPSK in fading channel, and what we assumed there is that the channel information is known to us, right. Now, we are going to look down into the performance of modulation schemes when we do not really require the channel information. It would be a good idea, because learning channel would be creating some overheads and some issues. So, before going to discuss the performance of PPM, which we will focus now in non-coherent channels, let us first ask the question, can we detect OK modulation scheme without having the channel estimates? And answer is no, because when you transmit one, let us say we transmit a signal A, and the energy that you would receive will be proportional to A square times G square. When you transmit 0, you transmit nothing, and then the received energy will be 0. So, where will be set threshold, assuming that this channel is hit with additive white Gaussian noise and these symbols are equiprobable symbols, the threshold will sit at A square G square by 2, and thus to take a decision, receiver must know what this G is, isn't it? And thus in these OK systems, learning channel is necessary, right. But now we are going to see the system or a scheme like PPM, where you do not have to know anything about the channel. Okay. So, in PPM, essentially what we have seen is that, let us say again we are focusing on binary PPM. So, let us say if we want to transmit 1, we transmit A and 0, and when we want to send 0, we will send 0 and A, right. So, in this is in terms of numbers. In terms of pulse position, you can think that if we want to transmit 1, we will send a pulse and nothing. So, this corresponds to A and 0, and when we want to send 0, we will send 0 and A. Okay. So, that is what happens in pulse position modulation. So, here we are saying this, if we want to transmit 1, or let us say XA, XA is defined as a combination of A and 0. That means, in first symbol time we will be transmitting A, in next symbol time we will be transmitting 0. Now, to transmit 0, we would be sending XB, where XB is combination of 0 and A. That means, in first symbol time we will be transmitting 0, in next symbol time we will be transmitting A. Now, we can define an observation Y, which is built using two observations Y0 and Y1, and looking on this Y0 and Y1, we have to take the decision about these XAs and XBs. Okay. So, that is the goal. Now, let us assume that we are transmitting this XA. Okay. This is what we assume. Now, what would be Y0? Y0 would be A times H of 0 plus Z of 0, okay, where Z of 0 is the complex number created by the noise in the first symbol time, okay, and H of 0 is the complex number created by the channel in the first symbol time. This Y0 is the sum of two independent complex Gaussian random variables. Complex or proper complex does not matter. So, because complex Gaussian random variables are always proper complex Gaussian random variables, and thus I have simply stated them to be complex Gaussian random variables, but you know that when I am saying complex Gaussian random variables, it simply means that these random variables are also proper complex Gaussian random variables. Okay. Y0 is sum of two independent proper complex Gaussian random variables, and thus Y0 is also a proper complex Gaussian random variable. Okay. So, if we want to find what is this variance of A times H naught, this is simply A square times variance of H naught, and we have already assumed that this channel has a variance of half in one real dimension. Thus, this will have a variance of 1 in complex dimension. Okay. So, variance of H naught is simply 1, and hence variance of A times H naught is A square. What is variance of Z naught? We know that noise has a variance of n naught by 2 in one real dimension, and because this is a complex Gaussian random variable, it will have a variance of n naught in one complex dimension. So, n naught by 2 times 2, because here we are thinking in terms of complex dimensions. Okay. So, what is variance of y 0? The variance of y 0 is simply A square plus n naught, right, because these are independent random variables, and thus the variance of y 0 is simply obtained by adding the variance of A h naught and the variance of z naught. What is mean of y 0? Mean of y 0 is A times mean of h naught plus mean of z naught, and this mean of z naught is 0 because it corresponds to a noise, and mean of h naught is also 0, and hence mean of y naught is 0. Remember, here we are taking mean of h naught and not mean of mod h naught. Okay. Mean of mod h naught will not be 0, but mean of h naught will be 0 because it is a proper complex Gaussian random variable. Now, if x a is transmitted, this is what we are saying, y 0 will be simply a proper complex Gaussian random variable with mean 0 and variance of A square plus n naught. Similarly, y 1 will also be a proper complex Gaussian random variable with mean 0 and variance of n naught, right. In y 1, what would happen in y 1? Y 1 is simply z 1, is not it? There is no signal present in this symbol 1. If hypothesis 1 is transmitted, which corresponds to x a being transmitted, and x a is simply understood to be a combination of a and 0. So, in symbol 0 you transmit a, and in symbol 1 you transmit nothing, and hence y 1 is simply z 1, and hence the variance of y 1 is simply n naught by 2 times 2, which is n naught. Okay. And hence y 1 is a proper complex Gaussian random variable with mean 0 and variance of n naught. So, from this we can derive the probability density function of y, which is defined to be composed of y 0 and y 1, and these two received numbers are also independent, and thus the PDF of y can simply be obtained by multiplying the marginal PDF of y 0 and y 1. Now, this is the marginal PDF of y 0. It has got a mean of 0 and it has got a variance of a square plus n naught. This variance is in complex dimension, and hence you do not have a term 2 in here. Okay. So, we have sometimes a term like 2 sigma square. Remember, then this sigma square must be in real dimension. If we are writing this variance in complex dimension, then we do not have to have this 2 in here, and hence this does not have a 2 in here. Similarly, you have 2 pi multiplied by sigma square in one real dimension. So, sigma square in one real dimension is simply a square plus n naught by 2, and again this factor 2 will cancel out. Similarly, you can find the marginal PDF of y 1, just the variance in this case is n naught instead of a square plus n naught. Okay. And multiplying these two terms, we can get the PDF of y. So, I can write this in this form. Okay. I have combined these two marginal PDFs and I have written it like this. Moreover, I define a constant c, which is just this thing, just to make my equations more compact. We will see that this does not influence my threshold. Okay. So, I have reduced this to a constant c. Now, when x is transmitted, PDF of y is simply this, we have derived this here, okay, just compacting the equation, and if x b is transmitted, my PDF of y will be this. What changes? In case of x b, we have nothing for symbol 0 and we have a for symbol 1, and hence the variance in this case is a square plus n naught, the variance in this case is n naught. The things that were different here is that the variance in this case is a square plus n naught and the variance here is n naught, because in x a we are transmitting a and 0. Okay. Easy. Now, the job is to find the log likelihood ratio. The log likelihood ratio is obtained by taking ln of the ratios of the PDF when x is transmitted and when x b is transmitted. Okay. Then you can divide the two PDFs that we have obtained. So, we have obtained these two PDFs, we divide these two PDFs, we take the ln of it and we get the log likelihood ratio. So, when you divide this PDF by this PDF, you get this thing. Okay. Then we just have to take the ln of it. It is trivial arithmetic, thus I will not do this. I think you can do all of this stuff. From this we can get the log likelihood ratio as simply this. Okay. The interesting thing here is, if I am assuming ML rule, then log likelihood ratio, if it is greater than or equals to 0, I can decide that x a is transmitted, that in this case would correspond to hypothesis 1 being transmitted, and if this log likelihood ratio is less than 0, then I would assume that x b is transmitted, in this case it would correspond to hypothesis 0 being transmitted. Okay. Remember, in maximum likelihood detection, ln eta is simply 0, okay, or threshold is 0. So, what we have to see is when is this log likelihood ratio is less than or equals to 0, and this corresponds to the situation when mod of y 0 square is greater than mod of y 1 square, the log likelihood ratio will be a positive quantity, and hence this condition translates to this condition, that if mod of y 0 square is greater than or equals to mod of y 1 square, then you consider that the symbol x a is transmitted, which corresponds to hypothesis 1 being transmitted, and if this is not the case, then you assume that symbol x b is transmitted, which corresponds to hypothesis 0 being transmitted. Okay. Now, you notice something very funny in here. Here the decision does not depend at all on the channel knowledge. So, you see y 0, you take the mod of it, you square this up, you receive y 1, you take mod of it, you square this up, and based on these two quantities you can simply decide whether the hypothesis 1 is transmitted or hypothesis 0 is transmitted. Here there is no dependence on G. Okay. Thus, what we have shown is, even if there is no channel information present in the case of PPM, we assume that we do not know the magnitude of the channel, we also do not know the phase of the channel, and what we have seen in that case, that threshold does not at all depend upon this channel knowledge. Okay. And we have seen in one of the previous lectures that log likelihood ratio is a sufficient statistic. Okay. Based on the log likelihood ratios, you can always take the decision. This log likelihood ratio does not depend at all on the knowledge of H. Okay. Now, from here we can find out the probability of errors, and to simplify arithmetic a bit, we make these substitutions. So, we say that u naught is simply mod of y 0 square, and this corresponds to a random variable capital U naught being mod square of random variable y 0. Similarly, we can define u 1 to be mod square of y 1, and this corresponds to a random variable u 1, which is equal to mod square of random variable y 1. Okay. The first thing that we would like to do is, we want to compute the probability density function of this random variable u naught in terms of probability density function of the random variable y naught. Okay. And we know that probability remains conserved when you want to go from one space to another space. So, this is the probability when I want to think in terms of random variable u naught, and this will give me probability when I want to think in terms of random variable mod of y naught. Okay. And I know what is this quantity. Okay. This quantity is simply mod of y naught divided by variance, and we know that the variance of mod of y naught is simply a square plus n naught by 2 times exponential minus of mod square of y 0 divided by a square plus n naught. Okay. And I have to integrate this thing over this numerical values y 0. Now, if u naught is mod square of y 0, then d u naught is simply 2 times mod of y 0 times d y 0. Okay. Now, what I can do is, instead of dy 0, I can write this as d u 0 or d u naught divided by 2 mod of y 0. Okay. And instead of mod square of y 0, I simply write u 0, because that is what u 0 is. Now, this is simple, I can cancel this with this and I get this times d u 0, and this is what this is, right. And from here I get that probability density function of random variable u 0 is simply this. All right. Now, what is the probability density function of random variable u 1? Following the same steps, you can go to this. What changes in here is, instead of variance of a square plus n naught, you just have a variance of n naught, because we have seen that when x is transmitted for symbol 1, the variance is simply n naught. Okay. Now, the first thing that we have to see before we can arrive at the probability of error formula is what is the probability that this random variable u 1 has a numerical value larger than u. And we know how to solve this up. You simply have to integrate this PDF from u to infinity. This will give me the probability that random variable u 1 is larger than u. And solving this is pretty trivial. If you solve this up, you get that this quantity is simply exponential of minus u by n naught. Okay. This is what we will use. So, probability that u 1 is larger than u is simply exponential of minus u by n naught. Now, we can find out the probability of error when x is transmitted. When x is transmitted, there will be an error when u 1 is larger than u naught, because when x is transmitted, we are transmitting a n 0, and we hope that y 0 mod square is larger than mod square of y 1, because then the detector will assume that hypothesis x is transmitted. But if this is not the case, then you get an error. And when will this situation happen? When u 1 becomes larger than u 0. Okay. So, this is the probability of random variable u 0 taking in a numerical value small u 0. Okay. And when this happens, there will be an error when random variable u 1 has a value larger than u naught, and this probability is given by this. So, this corresponds to probability of random variable u 1 taking a value larger than u naught. This is what we have derived in here, and this is the probability of random variable u 0 taking in a numerical value small u 0. Okay. Now, we can integrate this thing up and we get probability of error when x is transmitted is simply 1 divided by 2 plus a square by n naught, and a square by n naught is also abno. Similarly, what we can do is we can find that the probability of error when xp is transmitted is also the same, right. There is no reason why the probability of error will be different when xp is transmitted, and hence the average probability of error will also be this. Okay. So, what we have done now is we have calculated the probability of error in case we have PPM scheme and we are using non-coherent detection. Now, let us see in totality the probability of error if we are using non-coherent scheme, if we are using PPM is simply 1 by 2 abno if we are using coherent systems, and this probability of error is approximately 1 by abno if we are using non-coherent systems. Okay. Thus, you lose out 3 dBs when you are going from coherent systems to non-coherent systems. What an advantage in non-coherent systems is that you do not have to learn the channel anymore, and thus the overheads corresponds to learning channel and errors in learning channel are not there. Okay. What we also see here is when you go from coherent systems to non-coherent systems, or you go from non-coherent systems to coherent systems, you do not improve your abno requirements considerably. I mean, we have already seen that when we had this coherent systems, the abno requirement was around 74 dB for BPSK streams, right. And by using non-coherent systems, you also have an additional 3 dB penalty, right. Thus, the problem in fading channels is not in learning channel. Okay. You might completely have the channel estimate, but it is not going to do you any good. Okay. So, now what we want to see is how we can reduce this probability of error, and to understand that we have to understand what is this deep fade. Okay. And before understanding this deep fade, let me draw Rayleigh PDF, which looked something like this. So, we have on this axis probability density function of, let us say, mod of h. On this axis we have numerical value of mod of h. Now, what you can notice here is that there is a very significant probability of mod of h taking in very small values. Okay. And thus, if your channel is in what is known as a deep fade, and we will see what does this deep fade mean, but let us just assume at this point that deep fade is the condition when channel is very badly behaved. So, when the channel is deep fade, it simply means that you have a very small value of this mod of h. Now, because of this very small value of mod of h, whatever abno you may have, the resultant abno at the receiver will be pretty small. Okay. And thus, by having a larger abno does not help you anymore. Okay. So, let us quantify what we mean by deep fade. So, deep fade is the condition when g square is less than 1 by SNR. Remember, we have seen that in BPSK systems, for example, we had a probability of error for a given g like this, right. Now, in BPSK abno is also SNR. So, I can also write this probability of error in terms of SNR like this. Now, when g square is less than 1 by SNR, this quantity will be less than 1, and because this is less than 1, you will have probability of errors, right. So, what we are saying, if g square is pretty small number such that g square times SNR is less than 1, we say that the channel is in deep fade, and if channel is in deep fade, whatever SNR you may have, because of this very small values of g, you are going to have errors. Okay. Let us investigate what is this probability of deep fade. So, we know that PDF expression is this, and deep fade will happen when g square is less than 1 by SNR, that means g is less than 1 upon square root of SNR. So, I have to find out what is the probability of deep fade by integrating this PDF between 0 to 1 upon root of SNR. And I can convert this expression to this expression by simply substituting g square as x, and everyone knows how to integrate this thing up. This is simply 1 minus e to the power minus 1 by SNR. And by using Taylor's series, I know that this is 1 by SNR plus some terms which are proportional to 1 by SNR square. If SNR is large, then this is negligible, and I get probability of defade as simply 1 upon SNR, right, or in this case this will also be 1 upon epno. Now, what we have noticed is that there is a striking similarity between this probability of defade, which is 1 upon epno, and the probability of errors, which was 1 upon 4 times epno, and thus you can relate that most of these errors happen because of this defade, right, and no matter what SNR you might have, because of this defade, the overall received symbol power or signal power is pretty feeble, and there will be errors happening because of that. Okay. So, you can only improve upon the performance by reducing the chances of the channel to be in defade. Okay. And to do that, what you can use are these diversity systems, right. So, in channel you have these two important properties. Every channel has got some coherence time, which simply means the time period over which the channel retains its statistics, and you also have a coherence band, which simply means that the band of frequencies over which the channel has the same statistical properties. So, again the coherence time simply means the time period over which the channel has the same statistical properties, and coherence band means the band of frequencies over which the channel has the same statistical properties. Thus, if a channel is in defade, you can transmit the signal in a different coherence band. Okay. So, for example, if let us say we have 3 coherence bands F1, F2 and F3, and if we know that the channel is defade in this band, I can use another band, right. I can use this F2 or F3, and thus I can reduce the probability of defade by choosing a band in which the channel is in good condition. The modulation scheme which does is for example CDMA. What happens in CDMA? You have the signal and you spread the signal across the entire bandwidth, and thus if one segment of the bandwidth is bad, or if the channel is behaving poorly in one coherence band, you have the another coherence band which will allow the receiver to have large values of signal transmitted. Okay. What you can also use is you can repeat the signal in time, so that you have less error rates when you are transmitting a signal out of the coherence time. Okay. For example, if my channel is bad in this time duration T1, I can transmit the signal, or I can repeat the signal transmission in a different time duration, so that in this time duration the statistical properties of channel might be good, and thus I can have small error rates. Okay. So, idea is either you extend transmission time of your signals, so that you make sure that the signal is spreaded in time such that in certain time regions at least it sees the channel in good condition, or you can spread the signal in frequency domain, so that you can transmit the signal in a frequency band where the channel is good. Okay. What you can also use, much more simpler to understand, is this idea of space diversity systems, where you create multiple channels between transmitter and receiver. So, in this case I have 2 channels between transmitter and receiver. Okay. So, I have 2 receivers and 1 transmitter. This is 1 by 2 space diversity system. If I assume that this channel is independent of this channel, I can say to a large extent that when this channel is in error or is in defade, this channel might be good. The probability that both these channels will be in error will be simply p square, where p is the probability of one channel to be in error. Okay. So, by having this multiple channels between transmitter and receiver, you reduce the probability of all channels to be in error simultaneously. Okay. So, for example, if you have L channels between transmitter and receiver, the probability of defade of all channels at the same time is simply p to the power L, where p is the probability of defade of one channel, and thus you reduce the probability of error. For example, if I have this 1 by 2 space diversity system, my probability of error reduces approximately to this value. Okay. So, probability of error when I just had one channel in case of PPM systems was this. If I have two channels, my probability of error will simply be obtained by multiplying the probability of error when I just had one channel two times. Okay. And here I have shown how does this probability of error reduces as we increase L. Okay. You can think this as bit error rate or symbol error rate, does not matter, because bit error rate and symbol error rate are same when we are talking about binary schemes. Okay. So, as I increase L, my probability of error reduces. Okay. And thus, by having large number of channels between transmitter and receiver, you can reduce the EBNO requirement to practical values. So, with this we have come to the conclusion of this lecture and of this course in digital communication. I hope that you have enjoyed this course and you have learned modulation, detection, and now you can think about the noise. Thank you.